Welcome everyone. In this lesson, we are going to study non-parametric tests, which are very useful when our data is not clean, not normally distributed, or not suitable for traditional parametric statistical tests. The title of this slide is The Architecture of Messy Data. This is a very important idea. In real research, data is often messy. It may contain outliers. It may not follow a normal distribution. Sometimes the data is not measured in exact numerical values, but only in categories or ranks. For example, in sports science, we may not always have perfect continuous measurements. Sometimes we may only know whether performance improved or not. In medical research, we may classify patients into groups such as recovered, not recovered, improved, or not improved. In social science, we may rank preferences instead of measuring exact values. So, non parametric tests help us analyze this kind of imperfect or non normal data. They allow us to work with ranks, categories, frequencies, and distribution free methods. In simple words, when the data is messy, non-parametric statistics gives us a practical way to still make meaningful conclusions. This slide compares two situations. On the left side, we see the parametric ideal. This means the data follows a normal distribution like a bell-shaped curve. In this case, we can use parametric tests such as the t-test, ANOVA, or Pearson correlation. But on the right side, we see the non-parametric reality. Here, the data is not normally distributed. It may be skewed, it may have clusters, it may contain outliers, it may not satisfy the assumptions required for parametric tests. Traditional parametric statistics usually depend on strict assumptions. These assumptions include normal distribution, known population parameters, independent observations, and continuous measurement scales. But in real world data analysis, these assumptions are not always satisfied. When we face dependent variables, unknown population parameters, ordinal scales, nominal categories, or non normal data, we need tests that do not depend on fixed population models. That is where non parametric tests become useful. A famous quote by John E. Walsh says that a precise and universally acceptable definition of the term non parametric is not presently available. This tells us that non parametric statistics is broad. It includes many methods that avoid strong assumptions about the population distribution. So, the key message of this slide is when perfect statistical assumptions fail, distribution free takes take over. This slide clearly compares parametric and non parametric methods. Parametric tests assume that the data is normally distributed. They usually require known population parameters. They are mainly used for continuous variables. Their null hypothesis is often based on population parameters such as the population mean or variance. If the assumptions are satisfied, parametric tests are usually highly powerful. Now let us compare that with non-parametric tests. Non-parametric tests do not assume any specific distribution. That is why they are also called distribution-free tests. They do not require prior information about the population parameters. They can work with variables as well as attributes. This means they can be used for nominal and ordinal scale data. For example, if we are comparing exact height, weight, or reaction time, and the data is normally distributed, a parametric test may be suitable. But if we are comparing ranks, categories, preferences, or non-normal scores, then a non-parametric test may be better. The null hypothesis in non-parametric testing is usually free from population parameters. Instead of testing only exact means, these tests may compare medians, ranks, frequencies, or distributions. So parametric tests are powerful when assumptions are satisfied. Non-parametric tests are less powerful in some cases, but they are more flexible and practical for real-world research. This slide presents non-parametric testing as a balanced scale. On one side, we have the advantages. These are versatility and simplicity. Non-parametric tests are usually simple to understand and apply. They do not require complicated sampling theory. They do not make strong assumptions about the parent population. They can operate effectively on nominal and ordinal data. They are also useful when sample sizes are small or when data is difficult to measure exactly. For example, if we only know whether a treatment improved or did not improve a patient's condition, we can still analyze the data using a non parametric approach. On the other side, there are some costs. Non parametric tests may be less statistically efficient than parametric tests. When we convert actual numerical values into ranks, we may lose some information. For example, the values 10, 20, and 1000 may become first, second, and third. This ranking removes the extreme size difference between 20 and 1000. Also, non-parametric tests may require larger sample sizes to reach the same statistical power as parametric tests. Some tests may be difficult to compute by hand, when the sample size is large. So the trade-off is clear. Non-parametric tests give us flexibility and simplicity, but we may lose some power and detailed numerical information. This slide explains one of the most important ideas behind many non-parametric tests, ranking. Look at the examples shown here. We have raw absolute values such as 5, 20, and 1000. In the original data, 1000 is extremely large compared with the other values. It is an outlier. But when we convert these values into ranks, we simply label them as first, second, and third. The actual size difference becomes less important. What matters is the order. This is why rank-based tests are useful when data contains outliers or is not normally distributed. For example, in a parametric test, one extreme value can strongly influence the mean, but in a rank-based non-parametric test, that extreme value only receives a rank. It does not dominate the analysis as much. This is the secret engine behind many non-parametric methods. They transform absolute numerical values into ordered ranks. Then they test relationships or differences based on relative position rather than raw magnitude. So, ranking helps us reduce the effect of outliers and focus on the order of observations. This slide works like a decision map. It helps us choose the correct statistical test. First, we ask, is the data normally distributed or not normally distributed? If the data is normal, then we usually use parametric tests. For example, we may use t-test, ANOVA, or Pearson correlation. But if the data is not normal, then we move toward non-parametric tests. Next, we ask what type of problem we have. If the data is categorical, we can use the chi-square test. If we are comparing differences between paired observations, we may use the Wilcoxon signed rank test or the sign test. If we are comparing two unpaired or independent groups, we may use the Mann-Whitney U test. If we are comparing more than two independent groups, we may use the Kruskal-Wallis test. If we are measuring correlation using ranked data, then we use Spearman's rank correlation. So this selection matrix is very useful. It tells us that the correct test depends on three main things: the distribution of the data, the type of data, and the research design. In simple words, before selecting a test, always ask, is the data normal? Is the data categorical, paired, unpaired, or ranked? How many groups are being compared? Now we begin with the first non-parametric tool, the chi-square test. The chi-square test is mainly used for categorical data. It is very useful when we are analyzing frequencies or counts. For example, we may want to know whether survival is associated with vaccination, whether gender is associated with product preference, or whether treatment group is associated with recovery status. The core idea is simple. We compare observed frequencies with expected frequencies. Observed frequency means the actual number we see in the data. Expected frequency means the number we would expect if the null hypothesis were true. The formula shown here is chi square equals the sum of observed minus expected squared divided by expected. Verbally, we say chi square is equal to the summation of open bracket observed value minus expected value close bracket squared divided by expected value. The formula is chi square equals summation of open bracket O minus E close bracket square over E. Here O means observed frequency and E means expected frequency. The degree of freedom is also important. For a contingency table, the degree of freedom is number of columns minus 1 multiplied number of rows minus 1. Verbally, degree of freedom equals open bracket C minus 1 close bracket multiplied by open bracket R minus 1 close bracket. In the anthrax immunization example, goats are divided into inoculated and not inoculated groups. Then survival and death frequencies are compared. The chi-square value helps us decide whether survival is associated with inoculation or whether the difference could be due to chance. If the calculated chi-square value is greater than the table value, we reject the null hypothesis. If it is smaller, we accept or fail to reject the null hypothesis. The second tool is Spearman's rank correlation. This test is used when we want to measure the association between two rank variables. It is the non-parametric alternative to Pearson correlation. Pearson correlation is used when data is continuous and normally distributed. But Spearman correlation is used when the data is ordinal, ranked or not normally distributed. For example, suppose students are ranked in science and also ranked in social studies. We may want to know whether students who rank high in science also rank high in social studies. Spearman's rank correlation can help us measure that relationship. The formula shown in the slide is rho equals 1 minus 6 times the summation of d squared divided by n cubed minus n. Verbally, we say Spearman's rho is equal to 1 minus 6 multiplied by the summation of d squared divided by n cubed minus n. Here it means the difference between the two ranks for each person or item. N means the number of rank pairs. The value of Spearman's rank correlation lies between -1 and +1. If rho is close to +1, it means there is a strong positive relationship. If rho is close to -1, it means there is a strong negative relationship. If rho is close to 0, it means there is little or no rank-based relationship. So Spearman's rank correlation is very useful when we are dealing with ranking systems, ordinal scores, or non-normal continuous data. The third tool is the sign test. The sign test is one of the simplest non-parametric tests. It is used when we only care about the direction of change, not the size of change. For example, suppose we measure performance before and after training. If a student improves, we mark a plus sign. If the student declines, we mark a minus sign. If there is no change, we record 0 and usually remove that pair from the analysis. The sign test does not use the magnitude of difference. It only uses the sign positive, negative, or 0. This makes it useful when quantitative measurement is difficult or when only direction can be judged. The slide shows the formula for the critical value k equals open bracket n minus 1 close bracket divided by 2 minus 0.98 multiplied by the square root of n. Verbally, k is equal to open bracket n minus 1 close bracket divided by 2 minus 0.98 times the square root of n. Here n is the number of non-zero pairs. The decision rule is also simple. If S is less than or equal to K, we reject the null hypothesis. If S is greater than K, we accept or fail to reject the null hypothesis. Here, S is the number of times the less frequent sign occurs. In simple words, the sign test asks, are positive and negative changes balanced, or is one direction clearly more common? The fourth tool is the Wilcoxon sign rank test. This test is used for pair or matched data. It is the non-parametric alternative to the pair t-test. The sign test only looks at direction, positive or negative. But the Wilcoxon sign rank test improves on this by considering both direction and magnitude. So it asks two things. Did the value increase or decrease? And how large was the difference? The procedure is shown in the slide. First, we calculate the difference between before and after values. Second, we take the absolute value of each difference. Third, we rank these absolute differences from smallest to largest. Fourth, we attach the original sign back to each rank. Finally, we sum the positive ranks and the negative ranks separately. The smaller total rank value is used as the test statistic. For large samples, the slide shows the Z formula. Z equals W plus minus mu divided by sigma. Z is equal to W plus minus mu divided by sigma. Here, W plus is the sum of positive ranks. Mulk is the mean of the rank distribution. Sigma is the standard deviation. The mean formula is mulk equals n times n plus 1 divided by 4. Verbally, mulk is equal to n multiplied by n plus 1 divided by 4. The variance formula is sigma squared equals n times n plus 1 times 2n plus 1 divided by 24. Verbally, sigma squared is equal to n multiplied by n plus 1 multiplied by 2n plus 1 divided by 24. The decision rule is if the computed W value is less than or equal to the critical table value, we reject the null hypothesis. So the Wilcoxon rank test is stronger than the sign test because it keeps some information about magnitude while still using ranks. The fifth tool is the Mann-Whitney U Test. This test is used to compare two independent groups when the dependent variable is ordinal or continuous but not normally distributed. It is a non-parametric alternative to the independent samples t-test. For example, suppose we compare the performance scores of two different training groups. If the scores are not normally distributed, we may use the Mann-Whitney U test instead of the independent t-test. The mechanism is based on ranking. We combine the observations from both groups into one pool. Then we rank all values together. After that, we calculate the sum of ranks for each group. The slide shows one formula. U1 equals W1 minus N1 times open bracket N1 plus 1 close bracket divided by 2. Verbally, U1 is equal to W1 minus N1 multiplied by open bracket N1 plus 1 close bracket divided by 2. Here, W1 is the sum of ranks for group 1. N1 is the sample size of group 1. Another formula shown is U equals N 1 N2 plus N2 times open bracket N2 plus 1 close bracket divided by 2 minus T. Verbally, U is equal to N1 multiplied by N2 plus N2 multiplied by open bracket N2 plus 1 close bracket divided by 2 minus T. Here T is the sum of ranks for the second group. After calculating U, we compare it with the critical value. If U is less than or equal to the critical value, we reject the null hypothesis. Otherwise, we accept or fail to reject the null hypothesis. The Mann-Whitney U test is especially useful for small samples and non-normal independent group comparisons. The sixth tool is the Kruskal-Wallis test. This test is used when we want to compare more than two independent groups. It is the non-parametric alternative to one-way ANOVA. For example, suppose we want to compare the operating time of three types of scientific calculators. If the data does not meet the assumptions of normality, we can use the Kruskal-Wallis test. The test works by combining all observations from all groups into one list. Then all values are ranked from smallest to largest. After ranking, we calculate the sum of ranks for each group. The formula shown in the slide is equals 12 divided by n times open bracket n plus 1 close bracket multiplied by the summation from j equals 1 to k of rj squared divided by nj minus 3 times open bracket n plus 1 close bracket. Verbally, H is equal to 12 divided by n multiplied by n plus 1 multiplied by the summation from j equals 1 to k of rj squared divided by nj minus 3 multiplied by n plus 1. Here, H is the Kruskal-Wallis test statistic, N is the total number of observations, K is the number of groups, Rj is the rank sum for group J, Nj is the sample size of group J. After calculating H, we compare it with the chi-square critical value using K minus 1 degrees of freedom. Verbally, degrees of freedom equals K minus 1. If H is greater than or equal to the critical value, we reject the null hypothesis. If H is smaller, we fail to reject the null hypothesis. So the Kruskal-Wallis test helps us compare multiple independent groups using ranks instead of raw values. This final slide summarizes everything into a practical selection guide. If we have independent data in two groups, we can use the Mann-Whitney U test, especially for ordinal or non-normal continuous data. If we have independent data in more than two groups, we can use the Kruskal-Wallis test, which replaces one-way ANOVA when assumptions are not met. If we have paired data and two groups, we can use the sign test or the Wilcoxon signed rank test. The sign test uses direction only. It checks whether changes are mostly positive or mostly negative. The Wilcoxon signed rank test uses both direction and magnitude. It is usually more powerful than the sign test when its assumptions are reasonable. For special cases, if the data is categorical or frequency based, we use the chi-square test. If we are studying rank-based correlation or association, we use Spearman's rank correlation. The key message is this: non-parametric methods sacrifice some absolute magnitude, but they gain broader applicability. They allow us to analyze data that does not follow normal assumptions. So whenever you select a statistical test, do not choose randomly. First, understand the structure of the data. Ask whether the data is normal or non-normal, paired or independent, categorical or ranked, and whether you have two groups or more than two groups. That is how we choose the correct non-parametric test.